talk in this session, Ernst Larsson, please. And 20 minutes including the questions. So we'll be a little bit late for the lunch, but there is plenty of time for lunch break. So,
or I will try to speak
no rush.
We'll see. Okay, so just this thing works. Yes, it does. Okay, perfect. Thank you very much for the introduction. So I will be giving a talk here on some solid state studies with SCEPIC, as I called it, but I think that this time we just show the fact that I'm a very arrogant person, because obviously it should be and open multipole, because open multipole is really the heavyweight here. SCEPIC is just about generating the electrostatic embedding. So I apologize for my arrogance. Okay, right. So I'm going to talk about ionic crystalline solids, and I will be doing an embedding approach in this field. Of course, a lot of you know that periodic density functional theory is probably the main player in this field, but it comes with some problems, and it's usually simpler if you want to do wave function theory to target this with an embedding approach. Because normally you will just try to reformulate your one electron Hamiltonian using some hopefully intelligent scheme. And if you reformulate your one electron Hamiltonian, it will be available to all of your electronic structure methods in the code. So it doesn't matter if you want it to DFT, coupled cluster, cuspt2, you can usually do whatever you want. And SCEPIC, which is the code that I have written and been working with, is all about ionic solids. So it's electrostatics and something called AMPs, and I will talk a little bit more about it later. Yeah, strictly ionic materials, this does not work at all for covalent materials, so no point in even going there. And as I said, open multipole is of course the heavyweight lifter for electronic structure calculations. I gave a similar talk at the last open multipole developers workshop, so I will probably skip a few details this time, so I apologize for that in advance. The wrong direction. Okay, so electrostatics. If you have an ionic crystal, electrostatics is important, and you really want to have your crystalline field with modeling potential from a crystalline field well represented. And ideally, you should also try to cancel as many higher order multiple moments as possible over your entire structure, because they can introduce some spurious errors. If you're just interested in energies, dipoles are probably fine, but if you're interested in some other properties, higher order might be necessary. And to achieve this, we use the general purpose electrostatic embedding method, which was originally implemented in the ab-initio code, which is in multipole, but not open multipole, but is now available as a part of SCEPIC. And it has with this procedure, you can analytically place some auxiliary charges which will cancel these higher order multiple moments. In principle, the theory can do up to infinite order. So it's actually very useful. And since it's analytical, you have a very little user bias in what you're doing. It's pretty foolproof, so to say. Yeah, but then the big player here is actually the AMP part, because if you think about just placing some classical point charges around the QM region, this is usually a bad idea, and it would put some severe constraint on how you're constructing your cluster, because if you have anions on your border, for example, you might experience very big problems with electron leakage, for example, which is when your electron density just starts to smear out into the classical region, which you want to prevent. And AAMPs is a good strategy to prevent this. And effectively, what an AAMP is at least as we use it here, is as a form of pseudoatom where you freeze the core and the valence orbitals. So you have both core and valence orbitals represented in your AMP, but they are frozen. And by doing this, you can actually model a change repulsion. And by modeling this, you will just prevent this electron leakage and other effects. But I think electron leakage is probably the main player. And also these AMPs are represented, the charge of them is represented as a kind of S-type Gaussian or contracted series of S-type Gaussian. So they also have a finite volume, which comes into some play. And in the end, you end up with something which looks like kind of a volume model of your system. So you have some QM region in the center, then you have some AMPs, and then you have some point charges. This approach is very similar to something which you could call CAP-ECP approach, which you frequently read about, or at least I frequently read about this. But there are some nuanced differences which I think is worth to point out. In principle, it's the same concept. You replace something around your direct border, either you do AMPs or you do CAP-ECPs. But the advantage of an AMP is that you can actually freeze valence orbitals as well, which means that you can represent your anions in this way, which gives you a lot more flexibility in what you can do. This you can't do with a ECP. Also, normally, though you're not strictly required to do this, you tune your AIMP to a given material, which should in principle mean that you're doing something better than if you just take some gas phase ECP and use this as your border. Of course, in practice, I will not claim this will always be a better approach, but you could at least argue that it is theoretically a bit nicer. And SCEPIC is, of course, focused on AIMPs, but if you want to use CAP ECPs, this is actually perfectly possible with this code, so it's not biased in that sense. I've spent a lot of time benchmarking this approach, so I will just throw out the summary for you, and those who are really interested can read our paper in chemical physics, which I forgot to add a link to it, but it's published in chemical physics, and we have also submitted a second paper on this. And here we've done some extensive benchmark studies on some simple ionic compounds, and we have always compared them to periodic density functional theory calculations, and in general, it's actually quite good. I hope you will just take my word for this. Some suggestions, if you want to use this method, is that you make sure to saturate the bonds of all your important atoms in your region. So if you think that this is the part of your material which is most important, then the bonds should be saturated. The AIMP region should be around 6 angstrom thick, because then you will no longer see any differences with increasing or decreasing the size of this region. And of course, ideally, no element should be represented only as AIPs. So if you take magnesium oxide, you should not have, for example, magnesium fully represented as AIPs. You should actually have real magnesium in your system as well. You would think that's very obvious, but good to know. And of course, the downside with AIPs as they are implemented now is that they are completely non-polarizable. So if you want to study a property where a dielectric response is probably important, then this will not work. Not yet, anyway. But to move on to some results. Okay, so the first material I'm going to throw at you is cerium, though it's yttrium orthodamnate. Awful thing to say. This is a model laser system, which we have started to study a bit. And in principle, you take this awful looking unit cell and you replace one of these blue things on yttrium with a cerium ion. And since this is a cerium 3+, you really only have one single electron that plays any part. So at least if you look at this from a formal point of view, it's a 4f1 species. And this means that when you start to do your state averaging and everything, you only have to worry about doublet spin. You don't have to think about any excited spin states or anything, there's only doublet. That's the only possible solution. And normally in this type of system, you want to study all the FTD excitation spectrum, which in this case will also just be 12 states in total to average over, at least if you do not account for spin degeneracies and spatial degeneracies. It will be less when you account for that. A good thing with this system is also that you have some symmetries which you can exploit. So in the end, I did calculations using C symmetry. And of course, since this is a lanthanide we are looking at, I used CAS-PP2 and CAS-CSO or RAS-PP2 RAS-CSO. I also tested some different basis sets to see how stable the results are with respect to the basis set. And actually, I'm going to break one of the rules I just mentioned to you. So the results I will give you now is strictly for a cerium 08 cluster. So I have no real vanadine and no real yttrium. So we are working on this, but this is just some first set of test calculations. Okay, so now some awful spectrum. So the first thing is that these red lines here are the experimental results of this system. Wait, I actually skipped one now, I think. Yes, of course, active spaces. Always active spaces. It's very nasty thing when you work with multi-configurational theory. That probably takes a few weeks to start to have a good guess at what you're doing. The minimal active space you can think in this case is to just have the 4f and the 5d orbitals of the cerium, because that's the excitation spectrum we're interested in. What we noticed, however, was that we have to add some semi-core orbitals, and we also tested to add some virtual orbitals. Some of you will probably immediately react to the fact that we have no oxygen orbitals if we just go through this list, and that's because whenever I try to add an oxygen orbital into my active space, I got more and more cerium core orbitals from the relaxation, so they really seem to be more important. I would like to solve this problem, but I haven't been able to do this far without posing some nasty constraints. So I tested 5 active spaces in total here, or at least there are some class expansions, and I will just call them AS1 to AS5. and they're just more complicated the further down you go and get bigger and bigger. But in principle, we're always talking about only serial orbitals. I feel like this is going the wrong direction. Anyway, so back to this. Experimental, as I said, and these other lines are just the results for the different states that are involved in these transitions. And the first thing to notice is that if you just use this minimal active space, you get a completely different picture from all the others. So as soon as you add these semi-core orbitals, this picture actually stabilizes, and you can do pretty much whatever you want. Very little happens. Nothing, no big changes, but you can see that at least this state up here, when you add the semi-core, drops by almost 4 electron volts, which is huge. You can also see some effects on the order of the F states, which I assume being on from here. But yeah, but once you add these semi-core, not a lot happens. And you can see that some of these states are pretty close to the experimental, but for the moment, I can't explain why there are two peaks, two experimental peaks here. These could, of course, be different events or something, I don't know. They still have a pretty small cluster model, but there are a lot of things to explore here. And of course, the basis set comparison. So I'm going to briefly mention this, but I just wanted to see if this strange behavior or non-perfect behavior was a consequence of the basis set I chose, but it doesn't matter which basis set I try here. They all pretty much give the same picture. As soon as the semi-core is included, you don't really see any big difference between these basis sets. So it's clearly not a basis set error. It's either an experimental error or the fact that I'm using a too small cluster or insufficient active space. I don't know yet. But the point is that we can at least see some good trends with this already small cluster. And as I said, I'm looking at larger cluster models now. And also, hopefully, I will be able to use DMRG or something like that to try to extend the active space a bit more. Right. Another application that I'm working on is also when you have some oxygen diffusion on a magnesium 001 surface. So what you do is that you take an oxygen atom, you put it on the surface, and then you move it from one side to the other. And this is a very fundamental process in a lot of catalytic processes. And actually, it's a lot more complicated than it sounds like, because if you would look at the minimum energy pathway for this, you would actually have a singlet to triplet and then back to singlet crossing, if the rates would allow that. Of course, it's hard to say what is an experiment, but in principle, that would be the minimum energy pathway. So I did some geometry optimization using periodic DSP, because here it would be very hard to do this with the embedded cluster approach. And I used the improved tangent nudge listed band routine to map out the potential energy surface. In the end, I also used two different clusters just to see that some form of dimensionality, what happens if you have a small cluster and what happens if you have a large cluster. I also used DMRG here, both with QSMAKI and ChemPS2, because if nothing has changed since I last looked, we have no single DMRG implementation in OpenMultiples that can do both MCPD3 and PASPD2. You actually have to use different libraries, which is a bit annoying. And I used those basis sets here. Yeah, okay, so just a quick comparison to periodic results. And so here I'm just looking at periodic PDE, contra cluster PDE, to see if it actually matches us all. And what you get in the end is that for all of these different surfaces you have here, potential energy surfaces, the difference is less than 0.1 electron volts, which is, in my opinion, rather okay. You can probably get it better by being a bit more careful with how you construct some things, but in average, you get very close to periodic boundary conditions. So it seems like at the DFT level, this cluster is well represented of both of these. Okay, I think I will just give up on this because I do not understand how it works. Right, and back to active spaces, because this is not a configurational theory. We have one oxygen atom moving from on top of one oxygen to another. So in my opinion, the most naive active space to choose for this would just be to say that you have 3 oxygens and you take the 2p orbitals of these. What I noticed happened when I tried this active space was that actually in some points on the potential energy surface, you started to get some 2s orbitals into your active space instead. So I just threw everything in. But then this will actually give you some artifacts, which I will show you soon. So in the end, it turns out that to actually get a smooth description of this reaction, I have to throw in a double shell on all of these oxygens. And I did this in 2 different ways, either by them in RAS3 and allowing 2 electrons, or I use DMRG just to see what happens. And the first thing to show is just what happens with all of these different vector spaces, and this is of course very messy to read, but the only thing that is important to note is this very, very strange architecture that I can't explain. And this is what happens if you use these minimal vector spaces. For some reason, the class 2 calculation here just explodes. The class SCEPIC curves, which I'm not showing here, are smooth, but that happens. I do not know why. I've played around with different classification settings. I keep reproducing this thing, so something is very strange here. But if we focus on the green and the blue curves, which is for this double shell vector space using either RAS-52 or CAS-52 DMRG CAS-52, then you can see that you have a smooth curve. So that's good. But what also you can see is that they do not like perfectly match. And as far as I can tell, this is due to the fact that the DMRG wave function is simply a lot better around the transition point. And you actually see a lowering in total energies here at around 3 electron volts, comparing these points here, where the lowering is at 0.5 electron volts. So DMRG seems to actually be very important to get a good description of this reaction. Maybe you should throw in some other orbitals, but yeah, you need to use a pretty annoying active space. I think I will just skip that part. And in the end, we want to do a dimensionality study, and we want to see what happens if we enlarge the system, but also we want to nail down this spin crossing point. So I added more points with this net. So now we're still looking at the same reaction. I just throw in a lot more grid points in a sense along the reaction pathway. And what happens then with DMRG, if we start with that, the red curves, you can see that it's still pretty smooth going towards the transition states. But when I throw on dynamical correlation, which I did in the form of MCPDT here, you can see that it's still smooth for the trig state, which comes here. But for some reason, I get a very strange shoulder here, which I can't explain. But it appears, and I can't get rid of it. I'll try different settings, but it's that. I don't know if this is a real thing or if it's some strange artifact. But at least if I try to compare it with what I got for a smaller cluster, the points where I have those small cluster calculations, they all agree pretty well. So yeah, I don't know, but this is what happens. And I had actually thought about throwing in some thoughts here, but I will avoid that because this took longer than I had intended. So I will just end up with some acknowledgement now. So first of all, to Valera Verjasov for supervision. Marek Krasnitsky and Louis Secco, who provided me with some AAD implementation and made a lot of this project possible. Same with Peter Shushko, who provided me with the original implementation of EMBQ. And then Matthew Wolf for discussions on diffusion, and Stefan Knecht, who very quickly implemented NP, SSI, DMRG, and CPDT when I asked him to do it. So thank you for that.
I think we have time for a couple of questions.
Me? So you show these active spaces on the oxygen for the diffusion. What's the role of the magnesium?
It's hard to say. It would also be interesting to test it, but I already end up with pretty big active spaces, right? And what you have here, my speculation is that, but I confirm this, it's a bit hard to see with this resolution, but you have a small orange dot here, which is oxygen that's moving, and it's essentially moving in a straight line from one oxygen to another. So it's very hard to say what role orbitals on the magnesium would actually play here. You also have the fact that this is magnesium 2+, so you would either have to throw in some core orbitals or some virtual orbitals, and it's not really sure. I don't know. I could not find an active space where those orbitals were stable.
The valence magnesium.
Yes.
Because so normally when you do transition, you do magnetism, you actually look from the other side with the transition metal, and then the oxygen is like the decoration that actually do some super exchange mechanism.
Yes.
Now you want to look from the other side, right? You are focused on the diffusion of the oxygen. So
yes.
For you, the magnesium is the spectator.
Yes.
Yes. I think you can kind of throw it in there, because when you have the electrons on the oxygen, then one of them might pop into the magnesium empty orbital, also take the balance of the magnesium, and then they can spin the couple, and then this electron is moving further out into the oxygen.
Yeah, no, it could be. It's just that I ended up with the same problem here as in the first project that I skimmed through, that I always end up with very big active spaces, and then it's very hard to add more orbitals. I mean, here to get this stable just from the oxygen point of view, I have to have that's what is it? It's 24 orbitals already.
So that's why you have the MRG. I mean, I don't know how stable your MRG numbers are. I guess
Yeah,
people use it.
Yes.
Right? So,
yeah, but it's still pretty heavy. It's not a question that, I mean, I agree that in principle you can do this with the MRG, and you can probably use the CASCF as well if you want, but my problem is that I do not necessarily have the computational resources to go to even bigger than what I'm already doing.
Yeah, I'm not an expert in conceptual question. So my understanding, state relation is very non-local. And when you describe, let's say, heat and embedded in some environment, so essentially describing the contribution to the state relation. So could you comment on this or how justify it?
Could you clarify your question a little bit?
So I mean, just if you have separate lines.
Yes.
Let's so then I think partially one dimension, so the interaction between this time will be very non-local. So many agents would be interaction.
Yeah.
Different exchange mechanisms by a static relation. So
yeah, you are.
One, so,
yeah, you're essentially, if I understand it correctly, you're essentially asking me to motivate by a template here, but I will ignore an orbital that's in here.
in a sense, yeah, not in this system, more likely in the
yeah,
and such.
The general argument for this is that we think a lot of these processes are actually very local, and that you can really select a subset of your orbitals which are the active and play a big part, and then that in principle CASP-2 should be good enough as a sort of pseudo MP2 treatment of your surrounding. This is of course not necessarily true, and personally I would be more comfortable if we could do some other type of partitioning where maybe we do CASP-2 on this part which would are least local, and then couple cluster on the surrounding maybe to treat them a little bit better. It's not obvious. It can only be motivated by comparison with experimental results to see if it works or not, to be honest.
Yeah, probably it's just a matter of a discussion during the launch time. So let's thanks Ernst and all speakers from this session.